Welcome to demo video two on gradient boosting on our course B10 Python for AI. This is very much a beginner's video who are new to this area. So gradient boosting focuses on some structured data and can be used to create ensemble models, which means ones that apply different models to different data sets and thus have the optimal solution for these different data sets, but based on different models. What we're thinking of is having initially a weak model with a weak decision tree that's shallow, from which we get the residuals that we send to the next tree that trains on these residuals to try to overall gradually minimize the error across the set of trees as we repeat this process. So we calculate where the model went wrong, and the residuals is the sum of the differences between the predictions versus the actual values, and that is input for the next tree, which uses these residuals to try to optimize the model. This is scaled by a learning rate, depending on how fast we want the model, how much we want the model to vary. And basically we're taking many weak models to combine them into one stronger model. Key libraries for this are XGBoost, which is installed already. LightGM, GBM is also an effective one that can be very good for larger data sets. And there's also CatBoost as well, which can also work on strings. So we're going to think about the hyperparameters that are associated with this work for this task for us, the number of estimators, the learning rate, and the maximum depth that we want in terms of the number of trees that we want as well. And what we should be aware of is having a lower learning rate, basically a slower speed of regression and more trees is generally better than having fewer trees with a higher learning rate. So what we can do, we'll skip that and think about our gradient boosting approach here. So we're trying to take in our sequence data and consider our bacterial data and consider that we're learning iteratively from as we go through this process until we have a final weighted sum of all the trees and their errors. And our trees are split based on thresholds rather than distances. So each is independent from each other in terms of the scaling required. We're going to use XGBoost, and that will take in a particular number of estimators, a maximum depth, and a learning rate to apply this model. It will subsample the data, evaluating the log loss rate, and also takes up a seed at the start. We can then fit the model here, get the predictions from the model, and then print them out. So printing out our what we would get, and here what we get is very, very similar to support vector machines with subtle differences. It's slightly more compressed. You see there from the precision recall and F1 score that there's only tiny differences really and has a very, very similar output. We can also visualize this. So we can use a confusion matrix to play, so recycling our code from earlier to create it for XGBoost with a slightly different color scheme. What we'll get is something like this, where you can see that we have 151 and 149 that are correctly classified. 51 and 49, therefore 100 are misclassified in our model here. We can also take our data and like before, try to visually plot the difference that we see to give us an important score in terms of the what were the most effective predictors for resistance overall. What we're doing is basically a bar chart of the plots as we go along, and we'll get something like this at the end, where we see that the best predictor for this was the zone of inhibition. The growth rate in colony size were less effective at that. And that may be because the zone of inhibition had bigger differences between the groups. We can also specify the number of trees that we want to use and apply the XGBoost classifier based on that. So that's the number of trees it's going to feed in here to the variable nt. And we've maxed out that 3 and our learning rate of 0.1. We can fit the model and append the output and then visually plot that at the end. So you see as the number of trees progresses, the test accuracy is quite stable. The training accuracy does improve, but there's a circularity there. So the best test set is 0.752. So adding more trees won't really help us there. There's kind of a limit in terms of how much accuracy we can get for this particular data set. If there's a very large data set, we might find that it improves to an extent over time. So that concludes our demo video on gradient boosting. Please see the next demo video for more on deep learning.